Okay, great. So our next speaker is Aditya Savara from Oak Ridge National Lab. And he's going to be talking to us about kinetic parameter estimation using Bayesian parameter estimation. So Aditya, if you're there, please go ahead.
Thank you. Can you hear me okay?
Maybe if you could get closer to the mic a little bit.
Okay, is this better?
Yes, thank you.
Okay, great. I'm excited to have this opportunity today to present to you a vision of the future in which Checky-Poo is used for Bayesian parameter estimation. I've been working with Eric Walker on developing this software, and hopefully by the end of this presentation, you will see where Bayesian parameter estimation might be useful in your own research. I'll talk about the big picture, some general information about parameter estimation, a little bit about Checky-Poo, and Bayesian design experiments with a single slide at the end. So the big picture, at least for me, is looking at experiments and calculations for more accurate predictions. We're interested in activation energies, mechanisms, etc. We have guesses from previous experiments, density functional theory, linear descriptors, and other sources of knowledge. This prior knowledge has uncertainties, and there's an excellent focus in research right now of trying to minimize those uncertainties as much as possible. However, even those uncertainties themselves are valuable. And so what I'm going to argue in this talk today is that we should be using those uncertainties, taking experimental data and their uncertainties, and computational data and their uncertainties, using them together to get the most physically accurate values. We'll be doing that with kinetic modeling, that is kinetic simulations, and Bayesian parameter estimation. So a simple example of parameter estimation using experiment and simulation together. This is a temperature programmed reaction experiment we're looking at here. And for those who are not familiar, we start with an adsorbate on a surface. We heat up the surface at a controlled ramped rate. So this axis is also time. Initially, molecules desorb. There's a maximum in rate for desorption because as molecules desorb, they're depleted. The rate goes back down, and that's a result of molecules being depleted until there are no molecules left. It's common in the literature to use kinetic simulations, varying the kinetic parameters, in this case, activation energies and pre-exponentials, to achieve as good of a fit as possible. But what happens when those fits are not physically realistic? What if density functional theory or other electronic structure calculations, sorry, is there a chat thing I need to pay attention to? Is there still a difficulty in hearing me? This is at...
Yeah, maybe if you can get a little closer to your mic again.
Okay, is this a difference again?
Yes, that's great.
Okay. So what happens when those estimates are not realistic? We can have different sources of knowledge, including density function theory, electronic structure methods, as well as other sources of chemical knowledge. I do want to point out that it's not only electronic structural calculations. There are also cases where, for example, you can have experiments that provide a Bronsted-Evans-Polanyi or Bell-Evans-Polanyi relationship, and that still has values and uncertainties. So what happens when we have an estimate from fitting that is not realistic because maybe our prior knowledge tells us it should be closer to 40 kilojoules per mole, but the fitting might say it's 10 kilojoules per mole? What do we do in this situation? Should we penalize the unrealistic fitting? And if so, by how much? My answer to that question is that we should not try to penalize the fit. We should change the question. With Bayesian parameter estimation, we change the question from what is the best fit to what is the most physically probable set of values. And this question has a well-defined solution. I don't want to go into the nuances of Bayes' theorem for the audience today, What I would like people to take away from this talk is there are two terms on the right. One of them is associated with the values of the observed data and the uncertainties. The other term here is associated with our prior knowledge, typically from density functional theory, and the uncertainties. On the left-hand side, we have our values that we're interested in estimating, specific values such as an activation energy, and we try to find them, at least in this talk, we look for the maximum probability. I want to draw this distinction that we are intentionally using the word estimation rather than optimization to emphasize that we're not trying to find the best fit, but the most physically realistic values. Now to look at a specific case, here's a case with ethanol desorption from serum oxide. As before, there's a peak. We have a maximum around 220 Kelvin in this case, and this particular peak is too broad to be described by a single first order reaction with a single activation energy. That means we can either look at more complex models with multiple states, multiple sites. We can also look at models where you simply have a dependence of coverage, dependence of the activation energy with coverage. I'm not going to show it to you, but I will tell you that if you use a single activation energy with a linear coverage dependence, you still cannot produce this peak. Now we're going to look at first a case with two states on the same type of site, where each state has a linearly coverage dependent activation energy. And the equations are not important for this talk. What's important here is you have some parameters and you get a rate. And we're going to compare CPE, conventional parameter estimation, and Bayesian parameter estimation. In this case, we have two activation energies and two pre-exponentials for this particular model. So first, we do a conventional parameter estimation where we try to minimize the weighted sum of squared residuals, weighted by the uncertainties in this case, and we do get a very nice fit. So we can call this a successful application of conventional parameter estimation. When we compare this to the Bayesian parameter estimation, we start with the physical knowledge of, in this case, 40 kilojoules per mole with some uncertainty for the adsorption strength of ethanol and serum oxide. We have our estimate of the pre-exponential ahead of time with some uncertainty, and we seek to find the maximum of the posterior distribution. And this is the output, which is a reasonable reproduction of the main peak. And this tail is at least in reasonable agreement, let's say, with having a shoulder like this. When we compare the two of them, you might ask the question, why do we use BPE if we get a worse fit? And what I'm going to show you here is indeed the main point I'm trying to make in this talk, is that the BPE result and the CPE result for state one both have physically realistic results as relative to our prior expectations of where physically realistic results may lie. But for adsorbate state two, the BPE result does give a data point which is in close agreement to the prior, while the CPE result is totally unrealistic. We have a pre-exponential that is beneath 1, this is a log scale, and we have a activation energy that's beneath 10 kilojoules per mole, maybe even beneath 5 kilojoules per mole. This should be joules. There's a misprint here in the axis. So the BPE values are more realistic than the CPE values. And now let's go to a more complex case. We can try to add in not simply linear activation energies. Previously, we had a constant in this gamma. So there was a linear dependence with coverage. Now we'll allow this gamma to vary as well, still in a monotonic fashion, so that we don't have a strictly linear dependence. Real adsorbate coverages are not simply linear. And by doing so, we can actually have enough flexibility to produce that peak shape with a single species at a single site. The conventional parameter estimation result, again, has a very successful reproduction of the peak. The BPE map is actually a better match than previously now that we have more flexibility in this gamma term. But once again, the CPE result is physically unrealistic. This is too low of an activation energy, and the pre-exponential in particular is quite low as well. Whereas the BPE result has a realistic activation energy and a realistic pre-exponential. One thing that greatly surprised me in this example is that both graphs, but in particular the BPE graph, requires a coverage dependence of less than 5 kilojoules per mole across the experiment. And the key thing, though, is that you did require a beyond linear coverage dependence for this result. We can look at the shape of the posterior. This is for the initial coverage of the reaction's activation energy. And we see that there is a defined shape. It's within a realistic area for the prior. And we can also get correlations between the activation energy and the pre-exponential. One thing I should make a point of is that all three of these figures came out of the Checky-Poo software. So these types of figures are produced automatically, as are these, as are the simulation results. So for this vision of the future, complexity is good and not bad. As shown in that example, we needed to have this non-linear dependence. And this is actually where the real strength of BPE comes in. Why? Because BPE seeks the most realistic solution from all solutions. So it's ideally suited for cases that would normally be classified as overfitting. Now comes an important question, which was asked about by one of the viewers in the earlier noted perspective article, which is, how do people perform BPE? Because people don't normally have the training for it. And to answer that question, this Checky-Poo software is being developed. We're going to have a tutorial for it that we're going to release as well. And it will be very close to plug and play. So the idea here is that we simply have to define our experimental data along with the uncertainties. We can build kinetic models. You can use a CSV file or Python. We already have a Cantera interface. I'd love to see an interface to the PyMut kind of software and other ones. It's actually quite general software. It's not limited to chemical kinetics, although that is, of course, what we're using it for at the moment. You have to define your priors as well, which in this context is going to be your typically density functional theory estimates, but it can be from other relations, etc. The uncertainties associated with them. And I should emphasize again that we do want to encourage complex problems because that's where BPE works well. And larger data sets that exist today in the literature and are being developed will give meaningful priors to put into that previous step. Finally, we do the simulations. We get posteriors out of the software. Right, and that's the whole process in a nutshell. So the intent here is that users don't need to understand what's going on under the hood. They don't need to understand the equations, and that's true for the following slides as well, that we can do things that go beyond parameter estimation. One of the things is design of experiments, and another is model discrimination. I'm not going to spend too much time on this slide, but the key point here is that if you have a particular set of parameters you're interested in, such as a difference in energetics between two states or an activation energy, etc., with Bayesian parameter estimation and design of experiments, you can actually assess what conditions are best to perform your experiment to get the most information. So in this simple example, which we'll put into our publication that's going to be forthcoming, that for these two temperatures, the 298 Kelvin temperature would be the better temperature to perform the experiment at because the distribution of the posterior in red is narrower, which means you get a more accurate, or sorry, more precise actually, the same accuracy, but more precise estimate, at least in this example, a more precise estimate of your parameter. In addition to design of experiments, there's also model discrimination. If you have two different models, such as two different reaction site types, or even two different mechanistic possibilities, and one is unsure as to which one is more physically probable, Bayesian model discrimination, also built in here, is going to be able to tell you for two different models which one is more physically probable. And one thing that I should make a small note of is that it's not always the model that produces a data point that's closer to experiment. That's not always the most physically probable. It's sort of like the same concept as the conventional parameter estimation, where the closest fit's not always the most physically realistic one. Sometimes you're getting a better fit at or better match at the expense of physical realisticness. So in summary, this software is one we're developing. We're quite excited about it. This was, at least my half of it, was sponsored by the Department of Energy. And with that, I will be happy to answer any questions.
All right, thank you very much, Aditya. We do have a few questions. We'll try to get through as many of them as possible. So the first question says that many times the reaction conditions are not properly controlled. Example, Reynolds number or temperature measurements, and several publications are made without control on these variables. How to discount this during the analysis?
You raised a great question, actually. And actually, this is a really appropriate question. So one thing that Andreas Heiden has made a big point of is that experimentalists are much less conditioned than computationalists to report the uncertainties. And one thing that would be very useful is if more uncertainties are reported in the literature. That being said, with sufficient knowledge, perhaps we can estimate the uncertainties in experimental data sets. And it's also good to know that you don't have to be exact about it. In Bayesian parameter estimation, as long as you have a reasonable estimate of the uncertainty, you want to go higher rather than lower, you can still perform the analysis. So that's a great question. One of the advantages is we can just analyze previous data sets with reasonable estimates of the uncertainty.
Got it. Another question asks, in conventional parameter estimation, you rely on the physical constraints that are clearly defined, but in this BPS, you're making a difference between 13 and 23 kilojoules per mole. One is right, the other is not. What is the basis to define these limits?
Another good question. One thing I want to note is that when you look at the Bayes theorem, this term, which is the likelihood, does correspond very much to the same things that you are optimizing in conventional parameter estimation. The second term related to the prior defines essentially, not with hard limits, right? These are not hard limits, but it does have a effect on the probability of what's most physically realistic. In this case, often from DFT. So you have a distribution of what you expect, and it's not a hard limit, generally speaking, but it is a distribution.
Okay, I'll try to combine two more questions while I start prepping the next speaker to share their screen. It seems that BP is dependent on parameters that you consider to be physically realistic. Does this presume that your prior knowledge of the system supersedes the result from your model fitting? How would that work for unknown or complex systems? And the other question I think you'll be interested in answering is, when will this software be available on GitHub?
Right, because if you go to that link, it doesn't show it to you yet. It's private right now. Let me answer that one first and then come back if there's time. We are in the process of making a publication, and again, by mid-2020, we hope to make it public. I'm willing to collaborate even earlier than that. We do want to, and I should have made this point more strongly, we would really like others in the community to contribute to the software as well. Not just potentially in advance, but more importantly, once it's public, because that will simply make it a more strong package, and we are all for that. The other question, just to answer it very succinctly, given the time constraints, it is very important to have priors. You must have guesses. When your priors result in a ill matching result, that's actually a sign that the model is a bad model. So you get information even in those cases. I'm sure we're out of time now, but thank you for those questions.